A fair die is rolled repeatedly. Let X be the number of rolls needed for a 5 and Y number of rolls for a 6. Find expected value of X given Y equals 2. So X is the number of rolls needed to get a 5. And what they are trying to say is X is the number of rolls needed to get the first 5. And that means that X has a geometric distribution with parameter P, where P is the probability of success in each trial. So here, since the probability of getting a 5 in each roll is 1/6, so P is 1/6 here. And also remember, we talked about it earlier in an earlier problem, that the expected value of a geometric distribution is 1 over P. And so it would be 1 over 1 over 6, which would be 6. And that is a fact which will be needed later in the problem. Okay, so we need expected value of X given Y equals 2. So for that, we will need the corresponding probability function. And Y also has a geometric distribution. Y is the number of rolls needed to get a 6. And since we are dealing with a situation where Y is equal to 2, so that tells us that the first 6 happens on the second roll. And this means that, so this information is only used to get the information about the main variable. The main variable is X because the expected value we need is for X, and Y given 2 is just one fixed constant. And that actually will also help us in finding what's going on with X. Because if Y is equal to 2, that means that the first 6 happens on the second roll. So we therefore know that the first roll was not a 6 because the first 6 is happening on the second roll. So if the first roll was not a 6, then it was a 1, 2, 3, 4, or 5. And that is only 5 choices on the first roll. As far as X is concerned, for X, we are looking for the probability of getting a first 5. So we can say that 5 on the first roll, the probability of getting 5 on the first roll is 1/5 because the first roll is one of these 5 numbers. So maybe we can say probability 5 on first roll given Y equals 2. Okay. So we agree with that. And then the first 5 can happen on the first roll with probability 0.2. Now it cannot happen on the second roll because the second roll is known to be a 6, right? Y equals 2 means the first 6 happens on the second roll. So the first 5 can happen on the first roll. It cannot happen in the second roll, but it can happen on any roll 3, 4, 5, or so on. So it can happen either on the first roll or it can happen on roll 3, 4, 5, and so on. So the situation is tabulated below. X given Y. Remember, X is the number of rolls for the first 5. And if it's only one roll, which means 5 appears in the first roll, then the probability is 0.2 as mentioned here. And then it could happen on roll 3 or 4 or 5 or so on. And the probability of that should be 1 minus 0.2, which is 0.8, because this has to be the complement of the other one, since the first 5 either happens here or it happens here. So now in a normal problem, we have a fixed number here, and then it's easy to get the expected value. You just do this number times 0.2 and then this number times 0.2. But here we're not having a fixed number. So we use a different technique to get the expected value. So remember, we need this expected value of x given y equals 2. So one way to do it is to split it up like this. So the expected value of x given x equals 1, y equals 2, times the probability of this happening, which is 0.2 as here. X is 1 and y is 2. So the probability of this is 0.2. Or you could have expected value of x given x is greater than or equal to 3. Remember, x can be 1, 3, 4, 5, or so on. So 1 is a different thing because it has this probability, and then 3, 4, 5 is a different partition. So we'll lump them all together. So this is capturing the 3 or 4 or 5 or so on. And the probability of this happening is 0.8, like here. So in summary, expected value of x given y equals 2 will be the probability of x equals 1 given y equals 2 times the expected value of x equals 1, x given x equals 1, y equals 2, plus the probability of x greater than or equal to 3 given y equals 2, which is 0.8, times the expected value. So the expected value could be here or here, with this probability, 0.2 probability here and 0.8 probability here. So we know the expected value of x given x equals 1, y equals 2, is basically saying that the value of x is 1 then. So because this is when the 5 happens on the first roll, so x is 1, and so its expected value is 1 here. And this one needs to be calculated, the expected value of x given x is greater than or equal to 3. Now, if it was just the expected value of x, then that is 6 as we wrote above. So let's scroll up. So here we mentioned that x has a geometric distribution, so its expected value is 1 over p and hence 6. So now let's try to understand what this is. So when we say that the expected value of x is 6, it means we expect the first roll to happen, the first 5 to happen on the 6th roll. But when we add this condition that expected value of x given x is greater than or equal to 3, I mean, we don't even need y here. So normal expected value is x given x is greater than or equal to 1, because the first 5 can happen on the first, second, third, fourth, and so on. So the normal expected value is 6. But when we are saying that we know that the first 2 rolls, because this is what this is saying, if x is greater than or equal to 3, it is saying that there is no 5 on the first 2 rolls. So and then basically we are resetting the whole game, and we are saying that, okay, we are talking from roll 3 onwards, so it takes it will still take 6 rolls, because from roll 3 onwards it's still a geometric distribution. So who cares what happened in the first 2 rolls? So from roll 3 onwards it would take 6 rolls to get the first 5. Like in other words, we can think of this also as being memoryless, because it doesn't matter what happened on the first 2 rolls if you are thinking of rolls 3 onwards. First 2 rolls could be anything. So at any point in the game, no matter where you start, the So let's say you played the game 100 times, and then from that point onwards, you are trying to find how many rolls do you expect to get the first five. It will again be six. So at any point, it will be six. And now, since we already are missing the first two rolls, so if you want to look at it from the beginning, then two more rolls will be added. So, right? So there's no five in the first two rolls. So the number of rolls you expect to get the first five, given that you're already gone past two rolls, will be the expected value, normal expected value, which is six, and then you add on the two rolls. So that'd be eight. So now we have all the information to calculate this. So 0.2 times 1, as we already talked about, plus 0.8 times, and this expected value we just figured out was 8. 0.8 times 8, so that ends up being 6.6, which is choice D.